Alright, question 6. It's a circular motion question. Sitting on the edge of a merry-go-round, mass is 47 kilos, so M equals 47 kilos, and his centre of mass located at a distance of 1.9 equals 1.9 metres. From the centre of the merry-go-round travelling at a constant rate of rotation, one full rotation every 4.9 seconds. So from here, what's his tangential speed? So here we have to work out how far he's travelling. So the actual circumference is equal to 2 pi r, which is equal to 2 pi by 1.9, and that gives you 11.94 metres. But he's taking time is 4.9 seconds to travel that distance. So velocity equals distance divided by time, which is equal to 11.94 over 4.9, and that gives us 2.44 metres per second. What's the magnitude of the net force acting on Andrew? Okay, so this is a centripetal force question, mv squared over r. So we know that his mass was 47. We've just worked out his speed, which is 2.44. That's got to be squared. And his distance from the centre is 1.9 metres. So that just gives us 147.3 or 147 newtons to 3 sig figs, sorry, 147 newtons. Next, Andrew decides to move towards the centre of the merry-go-round such that his centre of mass is now 1.5 metres. So R has gone to 1.5, so it's decreased R. So decreased R. The merry-go-round is still travelling at the same constant rate of rotation, completing one full revolution every 4.9. So the gut reaction would be Fc equals mv squared over r, and if you decrease the bottom number, you increase the centripetal force. That unfortunately would be wrong, because if we decrease our r value in this instance, then that's going to decrease our velocity, and that will come out with a smaller centripetal force. So in this instance, it's probably better to work it out first and then compare. And there are two ways you can work it out. First one is quite simple. Fc equals 47 times by, now our velocity is going to be 2 pi times by 1.5 over the 4.9 squared over the radius, which is now 1.5. And that will bring you out with 115.5 newtons. So you can show that, and that's an explanation, and put some words around it too, of course, and that proves that it's a decrease. Or the next thing you could do, and this could be something you could put on your formula sheet, if Fc equals mv squared over r, and v equals 2 pi r over t, we know that frequency is 1 over the period of motion. So this becomes v equals 2 pi r times the frequency. So putting that into here, we get centripetal force equals mass by 4 pi squared r squared f squared over r. So that and that'll cancel. So you end up with centripetal force equals 4 pi squared m r f squared. And now looking at this, we can see that if the r value decreases, then essentially we've got a decrease in centripetal force. And there's our explanation for that one. Next one. So this is like the Kunst tube that we use. Okay. So they've done some measurements, changed different frequencies, determine the speed of sound in a gas, as shown in figure, comprises a clear plastic tube, which we know, fellas, we've done this before in class. The only thing we didn't do was put talcum powder in it so that you could see where it bunches up. So when the loudspeaker plays a pure tone, the sliding wall is moved until the volume reaches a maximum loudness, indicating that L matches the resonant frequency. The talcum powder provides visual confirmation because it forms a pile in the middle of the enclosed section, indicating there's a node. And that corresponds to lambda over 2. The class for students collect the following data and find the length. Okay, so then from there, on the grid provided below, plot the data from the table, include the scales and the units on each axis, draw a line of best fit. Okay, so 1 over L, so that's going to be L's measured in metres, so the unit for that's going to be per metre. Frequency we already know is measured in hertz. Right, so looking at this then, trying to find where the data is. That's okay. Where is the data? Sorry. 1 over L goes up to a maximum of about 7. So let's have a look. 1, 2, 3, 4, 5, 6. That'll do. So 1, 2, 3, 4, 5, 6, 7, 8. And then frequency goes up to about 1200. So 2, 4, 6, 8, 10, 12. That'll work for us. So 200, 400, 600, 800, 1,000, and 1,200. Okay. So now we've just got to plot the data. So we've got frequency of 165. So 165 that's about 100 there. So 165 is in there. So that's 0.92. So that's going to give us somewhere up around there. Now, you guys will do this a lot better than I will using the graphics tablet. So frequency 330. So that's 300. 350 is in there somewhere. And that gives us 1.89. So that's going to be up around about there. So I like to use crosses instead of circles or dots. Then 587, so that's close enough to 600 for this little rough diagram, gives us something around about there. Then we have 880 and 5.18, 880 and 5.18, so that's somewhere around there. And then we get 1175, so that's 1100 and 3/4, 1175, and very close to 7. And that gives us our data. So we've plotted the data now. We've included the scales. Now we need to draw in a line of best fit. So let's just say it looks something like that. Now, obviously, everyone's going to have a different line of best fit, so don't get too stressed if you talk to others and go, oh, that's slightly different to what I got. Next part says, determine the gradient of the slope in part A, show the working out used to obtain the gradient. Once again, because this is a line of best fit for you, then your values will be different. So let's say I use that one there, which is 1,000, 600, 600 as one of my data points, and I'm going to go 0, 0. I know I'm fudging it a little bit there, but let's run with that. So M equals change in Y over change in X, or Y2 minus Y1 over X2 minus X1. By forcing me to use the origin, that makes it nice and easy. So what were my values again? 1,600, so 600 minus 0 over 1,000 minus 0, that gives me a gradient of 0.6. Now the units, the rise, we had that as being units for rise were equal to 1 over metre, That was divided by frequency, which is per second, is hertz, because 1 over f equals t, so f equals 1 over t. So that ends up giving us our units in s per m. That's why they get that value there. So that's 0.6. Okay, so there will be a range, obviously, that will be accepted for that. So that's 6. Okay, so we'll use points 1000, 6, which is 0.006, 0.006. Use a value for the gradient part B to calculate the speed of sound in air. Okay, so from here, we have our gradient equals 1 over L divided by our frequency. So that gives us m equals 1 over f L. From there, we can go, we're told that L equals lambda over 2. So that means that m is equal to 2 over f lambda. Now we know that v equals f lambda, so m equals 2 over v, so v equals 2 over m, so 2 over our gradient. So therefore that's equal to 2 over 0.006, and that gives us 333 metres per second.